velocity time curve for 100 meters. You've all seen that in text and books. So somewhere, usually 2 10-meter segments, the athlete's at its fastest velocities possible. But you can see the rate of acceleration is pretty steep. You know, if we go 10 meters, 20 meters, so on down the track, it's pretty steep. But when we get up here, this is where the velocity, this top-end speed mechanics is occurring, and then most athletes decelerate or fade slightly through the end of the race. Now, there's some confusion. Some people really decelerate. Some don't decelerate as much. So it gives the aura to the spectator, to the fan, that people are accelerating all the way to the end. They're running away from people. What they're doing is they're pretty efficient. They're controlling the rate of deceleration. This person is not controlling the rate of deceleration. Is that because this curve was too steep and they burn all the fuel up? Is there bad mechanics here that are causing this? There's a variety of reasons why athletes fade at the end of the race. I think it's a mistake to always blame speed endurance for failure at the end of a race. Our statistics show we have some people that are unbelievable at speed endurance workouts, but they're down here. And when we measure them on film, they're making huge biomechanical mistakes, or their rate of acceleration is too steep for their genetics. So, an athlete that violates our page 1 comes out with a lot of frequency real early, and the stride length isn't increasing, is going to use biochemistry a lot quicker than a person doing it harmonically and efficiently. So a lot of times in the discussion of the literature, you hear about rate of acceleration or race distribution. We had a discussion last night. If you have a 400-meter boy that can run 47 seconds, and his girlfriend comes to the meeting, and he goes out in 21 seconds, he's probably not going to run 47, is he? It's going to be bad. Well, what did he do? He violated the rate of acceleration and the utilization of his energies in that race. Well, the same thing happens in 60 meters or 100 meters or 200 meters. The hardest thing to coach in 200-meter training is race plan. It's the most difficult project. What do you do the first 50? What do you do the second 50? What are your thoughts from 90 to 120? What are you doing when you hit the 150-meter mark? Well, one of the things that you can control is their mechanics. If they're more efficient, they got a better chance to weather these negative features. So in that, we look and talk a lot about posture, strike landmarks for the foot. Where is the foot striking in relation to the hips or the center of mass? Strike is a term we use for hitting something. Arm positions and angulations, leg angulations factor. In sprinting, we shorten a lever to allow it to speed up and recover. So when the foot comes off the ground, what happens to the heel recovery? Where are the limbs during these various components? Is it symmetrical? Is one side looking like the other side? Is it symmetrical behind the plane? What you see on one side, do you see on the other? We all have the kids with huge butt kicks and no knee lift. So we say, let's do more hip flexor strengthening. If they're striking the ground wrong or they're on the ground too long, they're going to have dysfunctional recovery mechanics. Backside's going to be in trouble. You could do hip strengthening exercises for years and it's not going to change if you don't change the mechanics. So in sprinting, when we look at world-class sprinters, when they block their arms and the lead leg, there's unique angles at the elbow joint. In the front plane, it's usually around 40 degrees. In the back plane, the elbow angle is around 120. This blockage, this stopping of these appendages creates weak forces into the ground, which gives us weak forces to project our body through space. They're called weak forces because the contribution of a split appendage is small, but at high velocity it can be massive. A small force transference at a high speed can be a big factor. So athletes that don't time the blockage of their arms, where both arms decelerate at the same instant, are losing mechanical advantage of weak force application.
And what direction? In the horizontal or vertical direction?
Well, when you block, the angle of your support base is the angle of the force transference. So wherever these hands block, if I'm here, 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 wherever I block, when I block my appendages, that force line is created. That's why if a person has anteversion of the hips and they're too far forward and they're striking the ground behind them and staying on the ground a long time, when they block, it's negative because they're increasing forward rotation. So what do? They arch their back to keep from falling, and then they complain about tight back and tight hamstrings. The mechanics are causing it. It's not about stretching more or seeing the therapist, it's about mechanics. Generally, as a rule of thumb, as the foot comes off the ground, the ankle increases in dorsiflexion, the heel comes to the buttock, towards the butt region, with the femur still at zero. That deceleration triggers a reflex in the front side for this to release. As this releases and blocks and decelerates here, momentum is transferred to the lower leg. The lower leg and foot swing out, puts a stretch in the hamstring glute apparatus, and that's what puts the foot down. So the position of what the arms are doing and what the legs are doing are very, very critical, because this is occurring in the flight phase. So we can hit the ground correctly at the right moment and everything, but if we're not repositioning our limbs to prepare to push or apply force again, then we're at a disadvantage. Does that make sense? Or is it going? Dorsiflexion paradigm. There's a lot of arguments about what does the foot or the ankle do in running. In my mind, a lot of research with people way smarter than me looking at elastic factors. I think the human body is a series of springs and pulleys. So when we land in sprinting, as the foot comes into the ground, it's supinated. It lands on the outside edge. As 5 toes plant, the heel touches real quickly, and then we pronate off the great toe. So it supinates to 5 toes, the heel touches to allow clearance, and then we pronate off. So looking at the symmetry of that, and we know that if the ankle and the toes are more dorsiflexed, when we hit, there's a greater elastic component for spring. So it may be worth exploring what is the ankle joint of your athlete doing in upright sprinting or in acceleration mechanics as they come from the block. If I stay on the ground too long, too far past my center of mass, or I apply force late, I'm going to get a lot of plantar flexion, pointed toe. All right? The gastrocs and the hamstrings are 2 joint muscles, so because of that elongated position, I'm reducing the efficiency of that 2 joint muscle system. I'm going to reduce recovery speed, my ability to get the leg back through and get ready to strike the ground again. Is everybody familiar with EMG, electromyographics? Anybody not? Anybody want a quick course? Okay. In the old days, the technology wasn't real good, so we had to sink needles deep in the muscles and have wires into fancy computers and the athletes on a treadmill, and it was pretty painful. So